Howdy, folks. My name is Arul Verma, and this week in CS128 Honors, we're going to be talking about structs. So our goals for today are to go over what a struct is, how you define and instantiate a struct, and how you use a struct. So let's start by asking what a struct is. So structs are custom-made data types that hold multiple values, much like tuples. And similar to tuples, you can hold data of multiple different data types without issues. And unlike tuples, you have to declare the type of the data that you are storing. So if you think back to the lecture that we had on basic data types, you'll remember that tuples and other data types that are built into Rust, you can implicitly declare what type of data you're storing. And that doesn't apply to structs. In structs, when you're creating a struct of like any type, you have to say what the different pieces of data you're storing types are. So if you look at the bottom right, we have active, our struct called user, and we have 4 different variables we're storing: active, username, email, and sign-in count. And for each different variable, we have explicitly declared the type of that variable because Rust doesn't know what type to fill in there. So you have to explicitly declare what type it is so that Rust, when you're creating that type, it can assign properly. So an object of the type struct is called either an instance of that struct or an object of that struct. They're interchangeable, and I'll be using them interchangeably throughout this lecture, but the common convention is to call it an instance. And functionally, structs are very similar to classes. So you'll also hear me refer to structs as classes very frequently. They are not necessarily the same thing. Classes are more encompassing than structs, but they have much of the same behavior. And some of this behavior that's shared is that instances don't share the same variables. So if I was to create 2 different instances of this struct user, and the first instance, let's say it's called user1, would not have the same value in its active as user2. And another functionality that they share with classes is that structs can also declare local functions using traits, or they can declare local methods with implement, basically. And another thing is that when you're creating a struct, they're declared prior to the method they're used in. And let's see how that looks over here. So we have our struct user that we talked about earlier, and we wanted to use it in main. So before our main, we place our struct user essentially as a global declaration that this is what struct user looks like. These are the variables inside: active, username, email, and sign-in count. And these are the data types of that data stored by our struct. So when we want to create an instance of that struct, we use the keyword let, as we do for all data, and then mute, name of data, and then we say equal to, because all structs are created with the constructor. So unlike other data types, you don't use the colon notation here. You use equal to, and then you use essentially a constructor type where you say user, which is the struct name, and then you fill in the different pieces of data. And you say like the colon notation implies data type to what the data is going to store, or sorry, variable to what the data is going to store. Now, another thing to note is that we have user1.email here. We're changing that email. So in tuples, you can't change individual pieces of data, but structs don't have the same restriction. You can change data. The only caveat being that you have to have that mute keyword used, much like you have to do throughout all of Rust. So keep that in mind that when you're using a struct, you can change data inside, and you can access or change that data using dot notation, as long as your instance is immutable. So as we said, if you want to access or change specific value in an instance, you use dot notation. And one thing to note is that you can't have certain values be immutable and others be mutable. You can't be selective. Your entire instance must either be mutable or must entirely be immutable. So like in our previous example, if we looked at it again, when we said mute user1, all email, username, active, and sign-in count are mutable. They can all be accessed and changed. And we can't selectively say, oh, let email be mutable, but the others won't be changeable. So that's not an option, even though other programming languages do support some sort of behavior like that. So another thing to note is that structs can be returned by functions because they follow ownership rules, much like other data types. So if we look at the functions build user below, both of which are valid declarations of a function, and they essentially do the same thing. The one thing to note is that they return a user. And this is possible because Rust supports what's called an implicit return, where if you don't explicitly use the keyword return, Rust will just return especially if you declared a return, like the object of the return type just before the end of your function, Rust will automatically return whatever you declare. So here we declare a user. So Rust will just automatically return this user. And because of how borrowing and ownership works, if you remember how that works from our previous lectures, this user, its ownership gets transferred from this function to the function that called build user. So this user doesn't go out of scope. The entire object will just get transferred and it stays in scope. So another thing to note is that if you look at our user declaration over here, sorry about that, we have our username string and our email string instead of &str. And this is something we talked about in previous lectures and we've put on Discord, the distinction between string and str. And this is very important here because in structs, you can't use &str because &str implies that you're borrowing data, the ampersand being the data, but the borrow. But structs are designed in a way such that instances have to own their entire data. So you cannot use &str inside of a struct. In fact, if you try and create a struct with &str inside, it'll error out saying that instances must have ownership over their data, essentially. So you have to use string if you want to have strings inside. So now another thing to note is I mentioned that both of these functions are equivalent, but they aren't the same. If you look at them just like going line by line, you'll notice that these two lines are different. So why do they work the same? Well, the reason they work is because of how struct initialization works. So first thing to note is that when we declared our user, as we went the intended way, we had user, we had our curly braces indicating our all of our data that we're going to put in, and then variable colon what we're going to put inside that variable, variable colon what we're putting inside that variable, and we comma separate through everything. But over here, we got rid of that colon and we got rid of that email. So which email is this referring to? Is this referring to the variable or the parameter that's being passed into build user? Well, the answer is both. Rust has a concept called field init, which is basically possible when the parameters that are being passed to your function are the same as the variable name inside the struct. So because we have a parameter called email and user has a value called email, user just reads that value email and it's like, oh, these are the same. So they're the same name. So I can just take the value from the parameter and put it inside the corresponding name. So email gets passed from the parameters straight into user's .email variable, and same with username. But because active and sign-in count both don't have corresponding parameters, you have to initialize those by hand. So now let's talk about how we were creating multiple instances of the same struct. So let's say we wanted to create a second struct that has all the fields be the exact same as the first struct. Now, typically this wouldn't really be an issue. We just copy the entire thing and then we change the corresponding line. So if we went with user one that we had declared over here, just keep this in mind, and then copying that code essentially over here, and we try to create user two. So we can see we essentially just copied user one. We said like active is equal to user one dot active, username two is equal to username one dot username, so forth and so on, right? So this works, but it's tedious because you had a struct with 100 pieces of internal data or 100 like data types that it's storing. This becomes a big problem because you have to go through each of the 100 lines and change it, and then that one or two that you're trying to make custom, you'd have to replace, which is a really annoying way of doing it. So these two pieces of code are essentially equivalent, and all they do is this one is the exact same thing, but with a concept called struct update, which is just where Rust understands that you're going to take the exact same data from a previous struct or a previous instance of a struct, and then you're going to replace a specific field inside that instance, and you're going to create a copy of it. So we have let user two is equal to, and then it's just user, curly braces, and then we say the line that we want to replace. So we want to replace email with another @example.com. So we replace it. And then this ..user one tells Rust, the compiler, that everything else, all other fields inside my instance, are going to be the exact same as user one. So we just put the second instance that we want to copy from here. And so Rust will change email in user two, and then it'll copy everything else from user one. So it's a very easy and quality of life way of doing essentially the same thing that's going on here, but just in a more quality of life way. So we talked earlier about how structs are similar to classes, but you'll notice in all of the examples I showed you, at no point did I ever have my struct contain a function declaration. And that's because if you try to declare a function inside your struct, you will cause an error. So how do we go about adding functions to our structs? The answer is through the keyword impl, or implement. So first we need this derived debug on the top, and then we have access to this keyword implement, which essentially just tells our compiler that whatever our struct was, I want to implement a function for that struct. Specifically, I want to implement a struct class function, essentially, which is accessed with the dot notation. So if I was to try and access this area function, and I'll go into more depth about like how we wrote this area function in a second, but if I was to try and access this, it would just be rectangle r is equal to new rectangle, essentially, and I'd fill in my width and my height, and then I'd say r dot area. So that would allow me to access that area function, and it's a class function because it's a function of that instance. So a few things to note about this is that first we have our impl rectangle, and then we have our function declaration, which takes ampersand self as a parameter. It takes a borrow of the instance as a parameter. So this allows us to access the data inside that function, or sorry, the data inside that instance. So when we had rectangle r in my example, let's say width was 5 and height was 4. Area needs access to those height and width values. So passing a borrow to yourself allows your function to access those values and then return 20. So that borrow is needed pretty much irrespective of the use of your method. And it works the same way with like a mutable borrow. So do understand how your borrows work because they're very important for your struct function declarations, your struct methods. So that's a key concept here that you need to have. And you need to understand that you're borrowing, so you can't change your data if it's not a mutable borrow. And that if you are borrowing with a mutable borrow, to be careful that you don't change your data and have data security issues. But yes, for all your methods inside your structs, you have to be passing borrow to yourself because that allows you to access the data and allows the impl to know that it's a method, not a associated function, which we'll go into in a second. So as I talked about just a few seconds ago, associated functions are the other type of functions that are listed inside our impl. So the key distinction being that ampersand self passes an instance. So our impl knows that all of our functions there are being passed as a method. So we access them with the dot notation. In contrast, our associated functions aren't associated with our instances. They're associated with the class itself. And the contrast there really comes when you realize how they're being used. So these functions aren't called by like dot notation, but they're called with colon colon. If you're familiar with like C++ or Java, those would be your constructors usually. So the keyword new takes their place, but when you're creating a constructor, it works the same way. So if I wanted to create a square where my height and width are the same size, so normally I'd have to create a new rectangle, and then I have to pass my size for height and then width, like assigning them in Rust. But alternatively, what we could do is set up this square, which all I have to do now is say rectangle r is equal to rectangle colon colon square, parentheses, and then pass whatever my size is going to be, let's say 4. So now I have a new rectangle where height and width are both 4. And the way I access this square function, this constructor, was rectangle colon colon square. And then I pass my size value. So another thing to note is that we still use self, but we aren't passing ampersand self. So that ampersand self tells, as I said, that it's not a method, it's an associated function. But this self here is not instance, it is struct. So the capital SELF refers to the struct that is being implemented for. So in this case, struct itself is an alias for rectangle, rather than alias for the instance of rectangle that we are dealing with. And this is most commonly dealt with for constructors, and generally you'll only be using it for constructors, but it can also be used for other associated functions, and I'd encourage you to look into other associated functions that you can make, because it can make your life really easy to have like some sort of global function for all of your struct instead of for your instances. So now let's bring up some interesting questions about structs. Say you want to compare two instances of your structs. Can you use equal equals as a comparator? Why or why not? And what is equal equals now that we're talking about it? Is equal equals a function? Is it an operator? And can you implement it? Like, can you change its behavior? Can you make it so that equal equals is only true if one value is greater than another. And on that note, how do you compare things that are more complex? How do you compare like tuples or vectors? How do you compare strings? Can you say one string is greater than another? Can you say one string is less than another? And what about not equals? So I've kind of thrown a lot of questions at you, but essentially it's just, how does comparison work? And I want you to pause for a second and think about it. Is comparison like a function-based thing? Or what does the computer do in order to allow for comparison? So I'm going to give you a few seconds to kind of just think it over. Feel free to pause the video here. And after a few seconds, I'll tell you the answers. Okay, cool. So let's think about it a little bit, right? When we're saying equal equals, what is the computer actually doing? Well, it's actually calling a function called EQ. It's a built-in function for almost every class, and it's implicitly declared. So in the case of structs, you have to declare your EQ, which is essentially your way of saying, I want to do some sort of equal comparison for checking equivalence. And you can do the same thing for not equals, which is NE. There's a similar for comparisons, but we don't really need to detail that at the moment. So when you want to implement your comparisons using your structs, for your structs, you'd still be using IMPL, your implementation. But instead of using derived debug, you'd be using derived partial equation at the top, which is just saying that I want to have access to the equation changes. So EQ, NE, comparators. And the way you set up or change your EQ functions is rather than just saying IMPL book, instead now you do IMPL partial equation for book. So you're telling your code that you're specifically trying to handle your equation portion for book. And one thing to note is that you can have multiple IMPLs inside your like for your struct. So you don't have to feel limited that like, oh, I need to declare my functions here, but I need to also have my equation at NE here. No, you can have one IMPL for just your function declarations, your methods. You can have one IMPL for your associated functions, and then one for your partial equations. That's totally acceptable. And Rust compiler allocates for that. It allows for that. So you don't have to worry about having like a single IMPL. So yeah, back to what I was saying about using your partial equation IMPL. So when you have IMPL partial equation for, in this case, book, then you declare your function EQ and or NE, depending on what you want to compare. And then you can create a custom comparator here. So notice that you are returning a bool because both EQ and NE, equals and not equals, use a Boolean check. So you need to make sure that you're returning a Boolean. That's very important. And the other thing to know is that you're passing your second parameter by reference, and you're also passing self, ampersand self. So you yourself are being borrowed, and so is the other person. So be aware of the fact that you are doing borrows, that you are accessing their data, you're able to view it, and make sure that you don't use mutable borrows, because in EQ and NE, you don't want to be changing the data itself. That's very important. So as I was talking about, I kind of referred to the code on the right, but now I just want to break it down a little bit. We have our struct book, where we have our ISBN, which is an I32, and a format, which is just a book format from our enum. The enum isn't really that important right now, so we'll kind of overlook it. The important part really boils down to the ISBN. So when you go to a library, you can say two books are equal, or they're the same book, if they have the same ISBN number. And that's how we check equivalence. So much in the same way, our FN for EQ takes the person who's calling it, which is the left-hand side of your equal equals, and the second item, which is your other, the right-hand side, and it takes ampersand and then capital S, ELF. That's important because it refers to the fact that you're taking a borrow of type book, not a borrow of an instance. You yourself are borrowing an instance, that's you, like the left-hand side. But the right-hand side is not, you're not borrowing the instance, you're borrowing your like other is your instance, and it's of type borrow class or struct. So be wary when setting this up, because the capitalization is very important here. Capital S refers to the struct, lowercase refers to an instance. And then you're returning a Boolean, and we're comparing the self's ISBN to others' ISBN. So, and that's the way we're checking for equivalence. And we can create a multi-level condition where we have like, we check if this is true, and then if this is true, we want to check if format's the same as well. And if format's not the same, then we return false. So you can have multi-level checks here. So this allows you to check for very specific things in your equivalence. You can check for multiple things in your equivalence. It's not limited, and you can have like a custom equivalence based off of that. So you don't have to feel limited when you're setting up your own equivalence versus where like an equal equals, for like arrays, every piece of value has to be the same. So that's a new way that you can set up comparators in Rust. So yeah, that's pretty much the end of lecture for this week. It's a pretty short lecture. We're going to be going more in depth on structs next week as well. So if you want to follow along, this week was chapter 5 on the Rust docs, and we kind of went over structs and methods. Partial equations aren't on the Rust docs. You might have to search that up independently, but you'll find Rust documentation on it, just not in the textbook. Homework 6 has been released, so feel free to get started and make sure you're on top of the homeworks, because I know they tend to pile up very quickly. And MP1 is due next week on Wednesday, so I'll be reminding you guys about that again next week, but make sure you're on top of your work. So yeah, please let me know if you have any questions, and have a great day. Thanks for listening, guys.